Euclid's first light. If you love the latest James Webb space images, wait till you see this. ESA's Euclid Space Telescope just sent back its first batch of images, and they're stunning. Called Euclid's First Light, this photo collection is a breathtaking tour of the universe's galaxies, and scientists are buzzing with excitement. These images challenge what we know about how the universe evolved, offer fresh insights into dark matter's role in shaping the cosmos, and let us peek into the past by capturing galaxies 10 billion light-years away. Plus, the photos themselves are incredible, especially the last one. From shimmering galaxies and swirling nebulae to star nurseries and rogue planets, Euclid has captured it all. Following James Webb, another super telescope has been launched. Euclid has opened its eyes, and what ESA's new space telescope has seen is shocking everyone. We have never seen so many galaxies in one place at such unprecedented depths and with such clarity. Euclid is expected to provide nothing less than definitive proof of the existence of dark matter and dark energy, while the images from James Webb once again cast doubt on the existence of both phenomena. Does this mean that the Euclid mission is doomed to failure from the outset? On March 19, 2025, the European Space Agency, ESA, published the first comprehensive data from the Euclid mission, a significant milestone for modern astronomy. The Euclid Space Telescope, which has been operating in space since July 2023, was launched with the aim of observing invisible dark matter and dark energy. The data now published includes breathtaking deep-field images in unprecedented 4K quality. These images not only show razor-sharp galaxy structures but also provide glimpses of regions of the universe that were previously literally shrouded in darkness. Among the images are famous objects such as the Horsehead Nebula, which appears in unprecedented detail thanks to Euclid's new resolution, and the Perseus Galaxy Cluster, a gigantic cluster of galaxies which is visible on a large scale for the first time thanks to Euclid. Particularly impressive about the telescope's performance is the sheer number of galaxies that Euclid has scanned and imaged in the first analyzed sections of the sky. In the first segment, over 26 million galaxies were identified, and that is still only a fraction of what the mission will capture over its planned 6-year lifetime. Some of these galaxies are up to 10.5 billion light-years away, which means that we are seeing them as they looked only a few billion years after the Big Bang. This also makes Euclid a kind of time machine that beams us directly into the structures of the deepest cosmic past. The enormous depth of data will enable researchers to reconstruct the large-scale distribution of matter in the universe, from which scientists hope to draw conclusions about the previously invisible dark matter. At the same time, analysis of cosmic structure formation should also provide clues to the true nature of dark energy. This mysterious phenomenon, which is believed to be responsible for the accelerated expansion of the universe, has not yet been proven from a strictly scientific point of view. With this first publication and the incredible images, Euclid has already demonstrated its scientific potential so impressively at its premiere that it's certain that this mission will open another door to a new era of cosmology. The goals of the Euclid mission are ambitious. In some ways, Euclid's mission sounds similar to that of the James Webb Space Telescope. However, the ESA is pursuing a completely different central scientific goal: to precisely map the large-scale structure of the universe in order to better understand the nature and distribution of dark matter and dark energy. Webb, on the other hand, is designed to image the first objects and structures of the young universe. Unlike traditional telescopes, which observe specific objects at specific points, Euclid is designed to create a systematic, large-scale picture of the development of cosmic structures across billions of light-years. The mission's main goal is to build a three-dimensional map of the distribution of galaxies in the universe, with the space telescope recording both the positions and distances of millions of galaxies. This distribution allows conclusions to be drawn about the distribution of dark matter, because although it's invisible, its gravitational pull influences the movement and accumulation of visible matter. Euclid can therefore indirectly measure where dark matter is located by observing how light from distant galaxies is distorted by gravitational lensing effects. Researchers call this technique weak gravitational lensing analysis. Another central goal of the mission is to study cosmic expansion, and in this respect, the mission is similar to that of the Webb telescope. However, Webb's instruments are not designed to directly observe the expansion of the universe. Dark energy is considered to be the driving force behind the accelerated expansion of the universe. There must therefore be observable connections between expansion and the movement and clustering of galaxies in the cosmos. After all, it was the movements of galaxies that led to the theory of cosmic expansion about 100 years ago. Euclid will reconstruct the history of cosmic expansion by measuring galaxy clusters and their redshift, thereby determining how the effect of dark energy has changed over time. The mission must proceed with the utmost precision. The instruments are designed to detect even tiny distortions in the light path. The initial data has already shown that the telescope's accuracy and calibration are sensational. The telescope's approach not only allows for precise measurements of the cosmic web and thus the large-scale distribution of matter in the universe, but also offers the opportunity to test the main ideas of currently competing and sometimes contradictory cosmological models in the long term. Euclid will provide a map of the universe and an immense database that, together with Hild's data, will help to clarify the two greatest unknowns in modern cosmology. We have no choice but to explore dark matter and dark energy in this data-driven way. Meanwhile, Webb's mission has provided further images that cast doubt on the existence of these two forms of energy and matter. Are the missions therefore in competition with each other? And what will happen if Webb finally proves that our entire old cosmology is wrong? Then the concepts of dark matter and dark energy could be off the table before Euclid has even presented its second data set. Are we dealing with a race between two telescopes? No, say the scientists. Even if Webb proves that the structure and nature of the universe is completely different before Euclid has completed its entire map of the universe, the mission will not have been pointless. A detailed and extremely sharp 4D map of the universe serves far more purposes than just proving the existence of dark matter or dark energy. The images will show billions of galaxies. The knowledge gained about their location, movements, and dynamics alone will provide valuable clues about the nature and structure of the universe, even beyond the dark spheres. Euclid versus James Webb Space Telescope. Which telescope is better? Even though the name Euclid is not as well known as James Webb at the moment, the mission will change our view of the world just as much as Webb's. The Euclid telescope and the James Webb Space Telescope are both groundbreaking observatories, and as we have already seen, they have fundamentally different missions. Euclid focuses on exploring dark matter and dark energy by mapping the large-scale structure of the universe and analyzing the effects of gravitational lensing. It provides precise 4D maps of billions of galaxies to understand cosmic expansion and the distribution of matter. In contrast, the Webb telescope has a completely different focus. It studies the earliest galaxies that formed after the Big Bang and analyzes the atmospheres of exoplanets to search for signs of extraterrestrial life. Thanks to its large mirror and infrared technology, the Webb telescope can look deep into the past and receive light from the first stars and galaxies. These two telescopes also differ greatly in technical terms. Euclid is primarily designed for optical and near-infrared observations, while Webb operates exclusively in the infrared range to see through cosmic dust. The orbital positions are also different. Euclid is located at Lagrange point L2, just like Webb, but the orientation of the instruments and the objectives of the two missions differ greatly. Euclid is equipped with a 600-megapixel camera and a near-infrared spectrometer to image large areas of the universe simultaneously. In comparison, Webb has specialized infrared instruments such as NIRCam, NIRSpec, and MIRI, which enable it to see through cosmic dust and study distant objects in great detail. Another key technical difference is the diameter of the mirror. Euclid's mirror measures 1.22 m, making it optimized for large-area mapping of galaxies. Webb, on the other hand, has a 6.5 m mirror that can capture significantly more light, making it possible to see very faint objects from the early universe. The expected mission duration also differs. Euclid is designed to operate for at least 6 years, while Webb is expected to operate for at least 10 years. These two are not competitors but complement each other perfectly. Both are invaluable to science. The three new ones, SphereX, Vera Rubin, and the Roman Space Telescope, Webb and Euclid are already superheroes of space exploration, but their achievements are still not enough to truly unlock all the secrets of the universe. NASA, ESA, other space agencies, and private investors are already preparing to launch the next generation of super telescopes. SphereX will likely begin searching for the building blocks of life this year. The Spectrometer for the History of the Universe, Epoch of Reionization, and ICE's Explorer is a NASA mission that will map the cosmos on an unprecedented scale. SphereX will also create a 3D map of the sky, but instead of imaging galaxies, it will make over 9 million line-of-sight observations. The focus will be on frozen substances such as water, carbon dioxide, and carbon monoxide, which are deposited on interstellar dust grains and may form the basis for the emergence of life. The mission will last at least 2 years and collect billions of data points. The Vera Rubin telescope will support Euclid and is also intended to shed light on aspects of dark matter. The Vera Rubin telescope, currently under construction, will be one of the largest ground-based observatories in the world. It is located on Cerro Pachón in Chile, a site with exceptionally clear nights and minimal light pollution. With an 8.4 by 24 meter mirror and a unique optical design, the Vera Rubin telescope will enable unprecedented mapping of the night sky. It's being developed specifically to study dark matter and help understand its distribution and impact on the cosmic structure. Scientific observations are scheduled to begin in late 2025. The Nancy Grace Roman Space Telescope is named after the researcher who was dubbed the mother of the Hubble telescope and is one of the most powerful next-generation space telescopes. It's scheduled to launch in the late 2020s and, similar to Webb, will focus on exploring dark energy, exoplanets, and the large-scale structure of the universe. Roman will be equipped with a wide-angle camera that offers a field of view 100 times larger than Hubble. This will enable it to map vast areas of the sky with high precision. Another highlight will be coronagraph technology, which will allow exoplanets to be observed with unprecedented directness and their atmospheres to be analyzed. Subscribe now and be there for every new video.